Hello, and welcome back to 4.3 lesson. Lesson 4.3. Okay, similar triangles and other figures. We're going to determine criteria for triangular or triangle similarity. How can we figure out if two triangles are the same? Or similar, not the same, not congruent. They're not congruent, but are they similar? Could I dilate one up into the other? What do I need to know? Inquiring minds want to know. What's the criteria? What do I need to know? Okay. What is the difference between the common usage of the word similar, like rectangles are more similar to each other than rectangles and triangles are, and the mathematical conventions for the word? What does it mean for two polygons to be similar? How can I prove or disprove that two triangles are similar? Let's find out. Two figures are said to be congruent if the second can be obtained from the first by a sequence of rotations, reflections, and translations. Also, all sides are the same, all corresponding. Same length, all corresponding angles are the same measure. But if all of the corresponding sides are the same length and all the corresponding angles are the same measure, then the second can be obtained from the first by a sequence of rotations, reflections, and translations. Previously, we found that we only needed three pieces of information to guarantee that two triangles were congruent. Either we knew the three sides were all the same length, that locked in the angles, so we got the angles for free. We had two angles and the side in between them, which actually locked in the triangle as well, so we knew all six of the sides and angles, three sides, three angles, had to be the same. Or two sides and the angle in between them. And we also had AAS, which we get because if you know two angles, you actually know the third angle in a triangle, because triangles always add up to, you know it, you love it. What about AAA? Are two triangles congruent if all three pairs of corresponding angles are congruent? No, we realized AAA doesn't work because the sides can grow and shrink without affecting the angles. Now they all have to shrink and grow together to keep the angles the same, but we can do that. We can grow all three sides simultaneously and preserve the angles. Those are supposed to be the same triangle. I think I failed. All right, whatever. I mean, similar. In this task, we will consider what is true about triangles that are similar but not congruent. Definition of similarity. Two figures are similar if the second can be obtained from the first by a sequence of rotations, reflections, translations, and dilations. This is a definition based on translations. I mean, transformations. Gosh, I confused those. It's been a while. Sorry, guys. It's late. I don't know if you can hear the custodians working in the hallway. Transformations. This is a definition based on transformations. Maybe we can obtain another definition kind of more similar to this one. Mason and Mia are testing out conjectures about similar polygons. Here is a list of their conjectures. Remember, conjecture is something we think is true, but haven't proved it yet. All rectangles are similar. All equilateral triangles are similar. Equilateral, okay, cool. All isosceles triangles are similar. Remember, to disprove something, you only need one counterexample. All rhombuses are similar. All squares are similar. I only drew one of each one, because obviously if I drew a second one, some of these conjectures would be rejected immediately. I don't even know why they're conjecturing some of this stuff. It's not even worth a conjecture. Which ones are true? Well, those are not similar because you cannot dilate one onto the other. These sides are the same length. So if you change this one's size, now the proportions are off. Right? Since this one's longer, it also needs to be bigger. Like this bigger one might be similar to this smaller one because the sides are proportional. If this side's twice as tall, this side's twice as long. But not this little one. So, disproven. All equilateral triangles are similar. Now this is interesting because all the sides travel together because equilateral triangles have all the same sides. So the proportions are always going to match. They're always 1 to 1. And the angle and equilateral triangles are always locked in at 60-degree angles, so the angles always match and the sides are always proportional. Ding ding ding, we have a winner. All isosceles triangles are the same. Well, again, we can draw two that are the same height but different size bases. If we scale this one up, what did I screw up here? Now the base is, oh yeah, I scaled this little one up to this size, but now the base is the same as this, but the height's not the same. So it's scaled up, the proportions on the sizes are different. Nice try, isosceles triangle. Rhombuses, this one is cool because you can do it without changing the size. You can just say, because like the equilateral triangle, the sides are all 1 to 1 because the rhombus has all the same size. But I will actually draw another rhombus with the same size sides, but I was able to flex the angles. So these are not, those are two rhombuses, not similar. Sorry, rhombi, get out of here. All squares are similar. Okay, this one's more like the equilateral triangle. Whoops. This one's more like the equilateral triangle in that the sides are all locked. And the angles are all locked. When I say the sides are locked, I mean that it's a 1 to 1 proportion between the two sides. And these ones also have 1 to 1 proportion between the sides. So however one side scales up, the other side has to scale up too. I pointed at different sides here. So the scaling up has to happen together. All the sides scale together in a square. The sides also scale in a rhombus, but we can change the angles without changing the sides. We cannot change the angles in a square because they always have to be 90. The equilateral triangle always has to have 60, so maybe that's a clue. Mason's explaining to Mia why he thinks conjecture 1 is true using this diagram. All rectangles have 4 angles. I can translate and rotate rectangle ABCD until vertex A coincides with vertex Q in rectangle QRST. Since A and Q are both right angles, side AB will lie on top of QR, side AD will lie on top of side QT. I can then dilate rectangle ABCD with point A as the center of dilation until points BCD coincide with points RST. Does Mason's explanation convince you that rectangle ABCD is similar to rectangle QRST? Based on the definition of similarity given above, does his explanation convince you that all rectangles are similar? Why not? What is he talking about? Well, let's follow it one step at a time. A to Q. So now you gotta imagine this square over here. We just took A to Q. Then he rotated. Did he say the rotate step? Oh, translate and rotate right there. He said translate and rotate. So swing this down. So now imagine the little square like this. This is B, C, D. Then he says dilate the square rectangle E1, ABCD, with point A as the center. Okay, A is here now, A prime, or A, depending on if this is like made of paper and you actually slid it over there. I don't know. Until points B, C, and D coincide with R, S, and T. Well, look, you won't have to dilate very far, maybe 1.2 scale factor till D is on T. But B will not be on R. So he is mistaken. There's the original one, and after dilating enough for D to be on T, this one's just hanging out. If we keep going, now D is way down here, but finally B has made it out to R, and good luck with S. So this doesn't, but his problem is these don't happen at the same time. Does not happen simultaneously. I don't know how to spell simultaneously. Hey, a heart for Valentine's Day. I'm recording this on Valentine's Day. Yeah. Does Mason's explanation convince you that rectangle ABC? We just said no. No. And we said why. That doesn't happen. Okay. Mia is explaining to Mason why she thinks conjecture 2 is true. So conjecture 2 was about... So the rectangles one's false. Remember, it didn't have to be... I don't know why they chose a square. It could have been, you know, this rectangle, and I gotta make sure it's not proportional. How can I make it not proportional? Okay, that's clearly not proportional. If you follow these steps, translate down, expand, the corners won't line up at the same time either. But let's try it for this one. So she says, translate, rotate ABC until vertex A coincides with Q. So A to Q. So now we have this guy. This is B, this is C. Then dilate ABC with point A as the center of dilation until points B and C coincide with R and S. B, C. Yes, that does happen at the same time because they start at the same length because they're equilateral, and they have the same distance to go because this one's equilateral. So, yay! Yes. The sides are proportional. No. No. Kind of already talked about this stuff. Sides are proportional because all the sides of the rhombus will scale together because all the sides have to be the same length, but angles can change from rhombus to rhombus. All squares are similar. Yes! Angles don't change from square to square. I wish we wrote square like this. Square. Square to square. But no, we have to write like this. Will always scale evenly because they are all the same length initially and still the same. After scaling, dilating, aka. Okay, enough of that silliness. Mason has another conjecture. Scaled drawings of polygons are similar figures. Yeah, if that's all you did is scale it, yeah. Aha. Corresponding angles of scaled drawings are congruent. Good, the angles have to be the same, or else it's not the same shape. And the corresponding sides of scaled drawings are proportional. Yes, okay, there we go. That is the other definition of similarity. If the angles congruent, sides proportional. What does sides proportional mean? Well, let's just peek back. Peeking into the Wayback Machine. I'll use this page. We didn't use this page. We made this basically on this page, but it's messy. So let's just use this nice clean page. We discussed that if this side scales down to half as big, then this side also has to scale down to half as big. That's proportional if the sides scale together. But also, we discussed that if this is 2/3 of this, then this corresponding side will also be proportional to this. Instead of saying this, let's say 1. But these can't literally be, this can't be 1 and this 1, because these are different sizes. So let's say this is, let's pick numbers for these. Let's say this is 9, and this is, well, we know, okay, this is 18. This is 9, because we know this little triangle's half. And if this was 2/3, then this would be 6, and this would be 3. And 6 over 18 equals 3 over 9 equals 1/3. Oh, because I screwed this up. This shouldn't be 6. Dang it. This should be 12. And this shouldn't be 3. This should be 6. It was still proportional, but just not the proportion I wanted. 2/3 is what I wanted. There we go, 2/3. So this establishes proportionality, that when you compare two sides on the same triangle, before and after, the proportion is the same before and after. Yep, we're going with betwixt. That means between. Proportion betwixt two sides is the same in both pre and post image. Proportional. That means it's proportional, is what I'm trying to say. And what's the other option? All sides scale scale the same amount. Yeah, there we go. All sides scale the same amount. Proportional. So there's two ways to establish proportionality. It's kind of fun, kind of funny. The triangles stay the same when compared to themselves, and if you do compare it to the other one, all sides compare the same. So you have two options: either compare it to the other one, and all the sides compare the same, or compare two sides on each triangle, and those comparisons stay the same. Okay. So that's to make sure the sides are proportional. But What about those angles? They have to stay the same too, right? The angles have to be congruent. Sides have to be proportional. Sides must be proportional. This is for similarity. For similarity. Sides must be proportional. Angles congruent. And we saw with the rhombus, remember the squishy rhombus? We had one rhombus and another rhombus with the same sides. So of course they're one-to-one proportions if they're the same, but we were able to change the angles. Those aren't the same angles. This one's squishier. Let me get even squishier. It's challenging. There, look at that rhombus. Proportional sides. In this case, again, all one-to-one proportions, but not similar. Not similar because of the angles. Similar because angles different. But here's what I'm trying to tell you. Triangles don't have so much freedom. Remember, triangles get locked in. Triangles, everything's connecting. Everything's connected. In triangles, everything's connected. Well, you might say, well, in this rhombus, everything's connected to each other. Well, not really. This corner doesn't touch this corner. This arm reaches out, and look, we could make both of these arms longer, and change this angle to make this angle even skinnier, and we haven't touched the other side of it. Yeah, this side's unchanged. Whereas in a triangle, well, whatever. In a triangle, this angle would be changing. Now we could leave the side the same, but these angles are getting messed with. But in the rhombus, we can leave this angle alone. Because not everything is directly connected in a rhombus, but everything is directly connected in a triangle. I wonder if that will become important any minute now. Indeed.